Hello everyone. In this video I'm going to provide you the solution to the second problem of the midterm exam for ROBT 303. Here we have the transfer function for the plant given as 7.5 times the s squared plus 2s plus 2 over the denominator, and the controller is in the form of a proportional one. We are supposed to draw the Root-locus plot sketch for this system for all values of k in R, meaning that we need to do it for the positive locus and negative locus. So let's first start with that point and then we will check the other ones. As the first step, we will form LOS, which is equal to GC times GP, and for that we will have 7.5 times K times S squared plus 2S plus 2 over S squared times S plus 3 times S plus 5. And we can write L now as rho times N over D, where rho is equal to 7.5 times K, N is equal to S squared plus 2S plus 2, and D is equal to S squared times S plus 3 times S plus 5. Looking at N and D, we will know that we have two zeros, which are at minus 1 plus j and minus 1 minus j. So we have a complex conjugate pair of zeros. And we have poles of the open loop system at 0 and 0, minus 3, and minus 5. So basically we have 4 open loop poles. N will be equal to 4. We have two zeros. N will be equal to 2. And as a result, R, which is equal to N minus M, will be equal to 4 minus 2, and it will give us 2. So R is equal to 2. This means that we will have two asymptotes for each of the positive locus and negative locus. And since that's the case, we can now think about finding the point of abscissa and the angle of the asymptotes with the real axis. For point of abscissa, we know that it will be equal to in the form of the sum of zi's minus sum of pi's over n minus m, where we have zi's coming from n of s, which will be in the form of s plus c1 times s plus c2 over s plus p1 times s plus p2, and so on and so forth. So for some of the zi's, we will have 1 plus j plus 1 minus j minus some of the pi's will come from 0 plus 0 plus 3 plus 5 over 2. And this will be equal to 2 minus 8 over 2 or minus 3. So XA will be equal to minus 3, the point of abscissa. For the angle of the asymptotes with the real axis, we will have R times KCA equal to 2h plus 1 times pi or 2h pi, where h will be equal to 0 and 1 for the positive locus and negative locus. And we know that R is equal to 2, therefore KCA will be equal to, if I replace h with 0 and 1, we will have pi over 2 and 3 pi over 2 for the positive locus, 0 and pi for the negative locus. So we have all the details regarding the asymptotes now. Let's start to prepare the sketches for our positive locus and negative locus. As the first step, we would need to draw the open loop poles and zeros of the system. So we'll use this for the negative locus. The poles and zeros of the system of the open loop system are located at the 0, -3, and -5. These are the poles of the open loop system. 0, -3, and -5. And we have two zeros at -1 plus -j. We can draw the asymptote. The point of abscissa that we have got is -3, and we have the angles. So there will be an asymptote like this for the positive locus, and the second one like this. And for the negative locus, we'll have it on the real axis. Now we can check the parts of the real axis that belong to the root locus. We can divide all the whole real axis into different segments from -infinity till -5, from -5 till -3, -3 till -1, -1 till 0, and 0 till +infinity. Now we can count the number of the poles and zeros to the right side of the segment. If I start from the bottom, for 0 till +infinity, we'll have 0. From -1 till infinity, we'll have 2 poles. From -3 till +infinity, 2 poles and 2 zeros, so 4. Then 5 and 6. This one has an odd number of the poles and zeros to its right side, so it will belong to the positive locus, and the rest will belong to the negative locus. So if I come back here, this part will belong to the positive locus on the real axis, and for the negative locus, these segments of the real axis will belong to it. We know that the branches will originate from the poles, from the open loop poles of the system. So we'll have one branch originating from the pole at -3, another one originating from the pole at -5. They will move towards each other. At some point, they will depart they will meet and then depart the real axis, and they will go towards infinity using the asymptotes that we have. So there will be a break away point, and it will be between -3 and -5. We have two poles at the origin, and since the area on the real axis nearby that point doesn't belong to the positive locus, both branches need to depart the real axis right at that point. So we'll have two branches departing the real axis at the origin, and they will eventually arrive at the zeros that we have here. We would need to find out to determine the exact value for the angle of arrival if you want to draw the precise, indeed, root locus plot. For the negative locus, we will have one branch originating from the pole at -5. It will go towards -infinity on the real axis. One branch will originate from the pole at the origin, and it will move towards +infinity on the real axis. The other branch will originate from the second pole at the origin. It will move towards the branch coming from the pole at -3. At some point, they will meet. They will depart the real axis, and eventually they will arrive at the zeros. We would need to determine the angle of arrival at the zeros. So beta arrival needs to be determined here. It might be pi, it might be minus pi over 2. If you want to draw the precise root locus plot, we would need to find out this angle of arrival, and to find that out, we would need to apply the phase condition at the vicinity of the zero that we see. The breakaway point here needs also to be found, but we know that it's already between -3 and 0. So you know that to find out the break-in and breakaway point, you need to solve m prime times d minus n times d d prime equal to 0. N is a second order polynomial, d is a fourth order polynomial, so out of this you will get fifth order polynomial for which you need to find out the roots. One of the roots will be at 0 because we know that we have a breakaway point over here. We are sure for that. So if you neglect that, you will be left with a fourth order polynomial, and the roots of that fourth order polynomial, two of them will determine the exact location for the breakaway points. But for the purpose of this example, this problem, we are not required to find the exact value. So we can just leave the drawing like this. Regarding the arrival angle, as I already mentioned, we would need to apply the angle condition and the vicinity of the 0. If you do so, let me draw it again here. If I apply the phase condition and the vicinity of the 0 over here, we would need to connect that test point to all the pose and zeros, find out the angles. So this angle will be 3 pi over 4. For phase of n, we will have this angle, which is beta arrival, plus this angle, which is pi over 2. For phase of d, we will have 2 times 3 pi over 4, as we have 2 poles at the origin, plus this angle, I call it theta 1, and this angle, which I call it theta 2, plus theta 1 plus theta 2. And I guess you can easily find the exact values for those two angles, yeah? As you know, that we have 1 here, 2 here, and 4 here. So once you have these values, you just plug them into the angle condition. Phase of n minus phase of d will be equal to 2h plus 1 times pi for the positive locus and 2h pi for the negative locus. And out of that, you can find out the angle of arrival to draw the precise, let's say, sketch for the Root-locus sketch for the system. But again, for the purpose of this problem, we are not required to find that value, the precise or the exact value for that. So we can leave the drawing like this. So having said so, we are done with drawing the Root-locus for this system. Let's go through the next points. The second point says that for which value of k, one of the closed loop poles of the system will be located at s equal to minus 4. So we know that s equal to minus 4 belongs to our negative locus. It might be even the breakaway point, but we are not sure about that. So minus 4 belongs to the positive locus. We need to apply the amplitude condition at s equal to minus 4. And since it belongs to the positive locus, this will be equal to 1 over rho. In order to find out the value of the rho and as a result the value of k. To find out amplitude of n over d at s equal to minus 4, we can either replace s with minus 4 in the expression that we have for n and d, or we find the distance between the test point minus 4 and all the poles and zeros of the system. I'm going to replace s with minus 4 in the expression that we have for n and d, but you can do it the other way around as well. So for n, we will have amplitude of minus 4 squared plus 2 times minus 4 plus 2 over minus 4 squared times minus 4 plus 3 times minus 4 plus 5, and this will be equal to 16 minus 8 plus 2 over 16 times 1 times 1, and this will give us 10 over 16, which is equal to 1 over rho, and therefore rho will be equal to 16 over 10. We will get rho equal to 1.6, and we know that rho is equal to 7.5 times k, so k will be equal to 1.6 over 7.5. With that value of k, one of the closed-loop poles of the system will be located at -4. In the next point, we need to determine the steady-state error for the unit ramp response of the closed-loop system with the k value that we have got from the previous point. For the unit ramp input, since we have a type 2 system, the steady-state error will be equal to 0 regardless of the value of the k that we choose. So it will be always equal to 0. So this point is quite easy to answer. Then the last point says that for which values of k the closed loop system will be stable. We can have a look at the Root-locus sketch that we have for the positive locus. You can see that for k bigger than 0, we never have a pole on the right half plane, so the closed loop system is always stable. For k smaller than 0, you can see that we have one pole always on the right half plane, so the system will be unstable for any negative value of k. And as a result, we can say that for k bigger than 0, the system will be stable. So answering this was also easy if you had drawn the Root-locus sketch of the system properly. Alright, so I think that's all for this video. Thank you for watching and see you in the next video.